Welcome back to The Explainer. Today, we're throwing on our systems engineering hats to look at exactly how we squeeze out centimeter-level mapping accuracy from our drones. I mean, if you've ever wondered how a drone can map a messy construction site or a huge topographical landscape with literal pinpoint precision, well, you're in exactly the right place. We're going to completely deconstruct the architecture of satellite navigation, look at the inherent flaws in the whole system, and then analyze how two specific technologies, RTK and PPK, step in to solve those critical errors. Okay, so from a systems engineering standpoint, our absolute biggest hurdle out in the field is simply distance. Our signal originates a staggering 23,000 kilometers away in space. By the time that signal travels all the way from satellite orbit down to our receiver here on Earth, it has lost an immense amount of its power. We're essentially trying to listen to a whisper from across a crowded, noisy stadium. It's just wild to visualize that immense journey. Our little receiver has to somehow catch this incredibly fragile whisper of a signal and then decode the complex message hidden inside. And because the signal is so incredibly weak upon arrival, it's highly susceptible to getting drowned out or totally distorted before our drone can even make sense of it. So here's our project blueprint. We're covering the anatomy of a GNSS signal, signal threats and frequencies, the drone mapping challenge, RTK, PPK, and finally, the engineer's verdict. Let's jump in. Section 1, Anatomy of a GNSS signal, the raw materials. Right, so before we can fix mapping inaccuracies, we really need to understand the raw materials our receivers are actually working with. A GNSS signal basically has three components. First, there's the slow-moving navigation data. This gives us low-frequency orbital info, like where the satellite is located in space and its clock corrections. Second, we have the PRN code, or pseudo-random noise. Now, this is a high-frequency sequence of zeros and ones, acting as a unique identifier. It allows our receiver to recognize specific satellites, even when multiple signals are sharing the exact same frequency, which is a clever trick known as code division multiple access. And finally, the third piece is the all-important RF carrier wave. This is a sinusoidal signal that physically transports the other data. And here's the kicker. When we need true survey-grade precision, we engineers don't just rely on the code. We actually measure the phase of this underlying RF carrier wave. Section 2, Signal Threats and Frequencies. Environmental noise. Remember how we said distance was a huge hurdle? Well, it isn't our only enemy. Once that carefully structured signal actually reaches Earth, it gets bombarded by environmental noise. Satellites transmit across specific L1, L2, and L5 frequency bands, and as engineers, we absolutely must protect this spectrum. But out in the real world, radio towers, electronic devices, even nearby heavy machinery can create electronic noise that completely bleeds into these bands, essentially blinding our drone's receiver. Section 3. The Drone Mapping Challenge. Seeking centimeter accuracy. Because of all these earthly attacks on our signal, a standard standalone GNSS receiver will generally only give you maybe 5 to 100 meters of accuracy. And let's be real, that simply isn't good enough for surveying, where a few centimeters can literally make or break an entire project. When we're designing a drone payload, we're absolutely terrified of something called cycle slips. See, when we're tracking that highly precise RF carrier wave, we need a continuous unbroken lock on the signal phase. If the receiver momentarily loses the signal, maybe due to interference or even just flying under a thick tree canopy, the phase accumulation breaks. This creates abrupt, nasty jumps in our positioning measurement. Those are cycle slips, and they are a massive disruption to precise mapping. To make matters worse, the signal doesn't always take a straight path down to us. Oftentimes, signals bounce off nearby buildings, structures, or even the ground before finally hitting our drone. This creates a chaotic situation known as a multi-path error. The receiver essentially ends up catching multiple, slightly delayed versions of the exact same signal. This heavily confuses the internal correlation system and actually artificially elongates the measured distance to the satellite. Now, add in the Earth's atmosphere acting as the ultimate unavoidable signal jammer, and the challenge just multiplies. As the signal travels through the electrically charged ionosphere and the dense, weather-filled troposphere, it actually slows down and bends. And that delay? It translates directly into distance errors. When you add up atmospheric delays, multipath errors, and potential cycle slips, honestly, it is a total miracle we can measure anything down to the centimeter. Section 4, RTK. Real-time precision, live corrections. So to solve these massive errors and achieve that miracle of centimeter accuracy, engineers develop two kinematic methods. First up is RTK, or real-time kinematic. The genius of RTK is that it uses a stationary base station placed over a known fixed location. Because the base knows exactly where it is, it can easily calculate the exact atmospheric and clock errors in the GNSS signals it's receiving. It then broadcasts these corrections in real time to the moving drone, which we call the rover, via a continuous radio link. Now, RTK is awesome because it gives you immediate corrected geometries right there in the field. But from a systems design perspective, it comes with immense logistical stress. Why? Because you absolutely must maintain an unbroken, constant radio connection between the drone and that base station at all times.
Section 5, PPK, Post-Processing, Offline Reliability.
Think about it. If you fly behind a hill or a big building and lose your live telemetry link, your RTK data immediately degrades back to standard, inaccurate GPS. No good. And that brings us to the PPK workflow, or post-processed kinematic. PPK operates on the exact same mathematical principles of using a base station to correct a rover's data. However, instead of broadcasting those corrections live, PPK just logs the raw GNSS data separately on the stationary base and on the drone. Then, after the drone lands, we grab both datasets and mathematically correct the trajectory in post-processing software on a computer. The beauty here? This completely bypasses the need for that fragile live radio link. Section 6. The engineer's final verdict. Choosing the right tool. So as a geospatial professional analyzing the system architecture, how do you actually choose your method? Well, both offer incredible survey-grade precision, but they really serve different operational environments. It's your classic engineering trade-off. On one hand, RTK provides near instantaneous corrections for immediate results. If you need to navigate to specific geometries in the field right now, RTK is for sure your tool. But it requires heavier logistics and perfect radio line of sight. PPK, on the other hand, drastically reduces field complications. By correcting the data offline, PPK offers extreme signal robustness over long distances and extended flights. In fact, because post-processing algorithms can look at the data both forwards and backwards in time, PPK often yields slightly better absolute accuracy than RTK. Pretty cool, right? Which brings us to our final systems test for you. Knowing the absolute fragility of a signal originating 23,000 kilometers out in space and understanding the constant threat of terrestrial interference and radio dropouts, consider this. If you were sent to map a dense, uncharted forest with zero cell service and miles of terrain to cover, which precision system would you trust to get the job done without fail? It's really a question of prioritizing real-time feedback versus bulletproof reliability. Keep exploring those trade-offs, and I'll catch you in the next explainer.